All right, when you think about an oil reservoir, what comes to mind? Probably a huge underground cave filled with black, sludgy crude oil, right? Well, what if I told you that's not even close to the whole story? The reality is way more complex and honestly a lot more fascinating. So today, we're going to break down the surprising ingredients that make up that deep earth cocktail. Right, so let's just jump in with that big question. If it's not some simple pool of oil, what are we actually dealing with thousands of feet below the surface? Turns out the answer is a wild mix of chemistry, physics, and a surprise ingredient that you are probably not expecting at all. Okay, to really get this, we've got to start small. I mean, really small, down at the molecular level. You see, everything we call petroleum is built from just two fundamental atoms, hydrogen and carbon. But it's how they link up that creates this incredible variety of substances. First up, we've got the alkanes. These are the most common family, so you can think of them as the basic Lego bricks of the petroleum world. They're super stable, saturated chains, which just means every carbon atom is holding on to as many hydrogen atoms as it possibly can. These chains can be super short, like methane gas, or they can link together into these long chains that form heavy, waxy solids. And this is where chemistry starts to get really, really cool. You can have two molecules with the exact same formula, say C4H10, but they're arranged differently. We call these isomers. It's kind of like using the exact same four Lego bricks to build a straight line versus a little T-shape. The result? You get two totally different substances, butane and isobutane, with completely different properties. One's used in your lighter, and its chemical twin might be used as a refrigerant. Now, what happens when those hydrocarbon chains decide not to stay in a nice straight line? Well, sometimes they loop back and connect to themselves, forming these stable rings. These guys are called cycloalkanes, or naphthenes, and they're another key piece of our petroleum puzzle. And finally, in our little tour of the building blocks, we have the arenes, also known as aromatics. Their claim to fame is these really stable double bonds between their carbon atoms, like you see in the famous benzene ring. They're called unsaturated because those double bonds mean they aren't holding the absolute maximum number of hydrogen atoms. They're a super common and important part of most crude oils. So you take all these different molecular building blocks, right? You mix them all together under immense pressure and heat for millions of years, and you don't get just one thing. Oh no, you get a whole spectrum of different fluids. So now let's look at how petroleum engineers actually classify this incredibly complex cocktail. The number one metric they use is something called API gravity. The easiest way to think about it is like a golf score for oil, where a higher number is actually better. A high API gravity means the oil is light and not very dense, which usually makes it more valuable. A low number means it's heavy and thick. So high number, it flows like water. Low number, it flows like molasses. This scale helps us map out the entire range of stuff you can find down there. At one end, you've got dry gas. It's colorless, basically just gas with no liquids. Then you move to condensate, which is a gas that, when it comes to the surface, actually drops out some really valuable light liquids. Then we get into the oils, volatile oils, and the classic black oil we all picture. And at the far other end of the spectrum, you have extremely thick heavy oil and tar, which are so dense they have almost no gas in them at all. Okay, so we've got gases, liquids, and waxes, all made of hydrogen and carbon. That seems pretty complete, right? But believe it or not, that's not the whole story. There's another major ingredient hiding in every single one of these reservoirs, and it's a big one. And that unexpected ingredient is water. That's right. Every single hydrocarbon reservoir on planet Earth also contains a huge amount of water, trapped right there in the same tiny pore spaces as the oil and gas. And I'm not talking about a little bit of dampness. This formation water can take up anywhere from 10 to a whopping 50% of the total space in the rock that's filled with fluid. It's a massive part of the puzzle that engineers absolutely have to deal with. Now, this isn't just regular tap water either. It could be ancient seawater that got trapped when the rock first formed, or maybe it seeped down from rainfall over millions of years. Its most important trait is its salinity, basically how salty it is, and knowing that is absolutely critical for engineers. It affects everything from how much gas can dissolve in the water to how they read their geological data. Okay, so why do we need to know all this stuff in such incredible detail? Why break down all the molecules, classify the fluids, and analyze the salty water? Well, for a petroleum engineer, Getting this right is the difference between a successful well and a very, very expensive hole in the ground. This knowledge is literally the foundation of everything they do. It all starts with step 1. Identify exactly what kind of fluid you're dealing with. Is it a valuable light condensate or a really challenging heavy oil? From there, they have to analyze all its unique properties. Only then can they figure out if it's worth any money and, finally, design the whole complex strategy to get it out of the ground. So the next time you find yourself at the gas station filling up your tank, just think about the incredible journey that fuel took. It didn't just start in some simple underground lake. It began as this complex, high-pressure cocktail of hydrocarbons in ancient water, where its very nature, whether it was a gas, a liquid, or a tar, determined every single step of its path, from deep within the earth all the way to your car.